So thanks for staying so far. The next session, I'm going to talk a little bit about co-design. This is multiple development projects, or covering multiple development projects that are aiming to create technology or drive technology toward exascale. I think after me we'll have Michael Feldman to talk about the HPC market view. So I think it's kind of a good connection to look into also how things or how the market is behaving towards the mutual goal of multiple organizations around to go to the exascale. And if time permits, we'll also plan to do a panel at the end of the day with some of the key presenters here to talk about exascale. So specifically talking about co-design architecture that enables or will enable us to drive into or toward the exascale era or exascale computing. So first, I wanted to start with giving you some global view or global perspective on the race to exascale. So I kind of just put a map of the world, basically, but there's multiple countries out there that are actively working now towards achieving the exascale. I'm not sure, maybe Michael, you're going to talk a little bit more about that or not, but from my information, and you might have some more information as well, there is multiple countries that already announced their plans. Japan announced their plan to go to exascale, with their goal is to be there in the 2021 time frame. I think there was also some announcement from Russia as well on some of their goals and plans. We know that China is putting efforts toward that. The recent letter from Obama and establishing the organization within the US also driving toward the exascale. You can start putting bets who's going to reach exascale first, but multiple countries around the world understand the benefits of achieving the exascale performance, what that can enable them from research perspective, technology perspective, and there's a lot of funding agencies that are actively driving technologies toward the exascale. So looking into the exascale and looking into one of the walls that we need to look into, how do we break in order to continue achieving performance improvements. And I'm taking a little bit to the history part. Looking 10 years ago, 15 years ago, at that time when we were moving to the terascale performance, there was a technology move from SMP machines to clusters. And I was trying to solve the issues of cost. Right, so if you want to build bigger systems, you want to continue in scale, having SMP architecture doesn't really allow you. You get a wall of cost of the systems. And then we saw the move from SMP to clusters. And with cluster technology, now it's made things easier to scale. And if you need more performance, you just add more compute elements or more storage elements, and it's easier to scale. You don't need to buy a complete new system if you want to get a little bit more performance. So that was a major change in the market. In the mid of the 2000s, we saw another dramatic change in technology, which was essentially moving from a single core to multi-core. Again, we got to a performance wall where you cannot achieve or cannot get more performance with increasing the frequency of the CPU, because you cannot increase the frequency of the CPU anymore. You go to the issues of power consumption. So the solution was to move from single core to multi-core. And that's enabled us to continue and scale and get higher and higher performance. And that brought us to the petascale era. And we saw the first petascale system that was built in 2008, which was kind of starting this era. And today we have multiples of petascale systems in the world. Now we're getting to another wall, which is, and I'm going to talk a little bit more on that, another performance wall, and we need to look into elements in order to try to continue and improving performance by 10x from generation to generation. So if you look on generations of all the components within the system, and we're looking into how do we get today from a petascale era to exascale era, you essentially need to grow 10x performance from generation to generation, which will take us to the exascale in the 2022, 2023, or 2024. So what's that item? And that item is code design. So we moved from SMP to cluster, single core to multi-core, and now we're talking about code design. DK mentioned code design as part of what he is doing as well, and there is multiple aspects of code design. So in a high-level perspective, code design is changing the approach of how do we look on the system itself, on the high-performance computing system. Today, every company, organization focuses on specific elements. There are CPU vendors focus on the CPU and try to improve just the CPU performance. Networking companies focusing on the network perspective. Storage company focus on a storage perspective. Essentially, in order to continue and scale the performance, you need to change the concept of how we design things. And instead of looking into a component by component, you need to look on a system level perspective. You need to look on the application side, on the algorithms, on the complete system perspective, and start to design from there. And the key element is with starting on a system perspective, and then from that point, leveraging every active element within the system to take part of the application itself. Now, code design has multiple flavors. At the end of the day, there is a flavor of software and hardware code design. And I'm going to a little bit focus on that one throughout the next few slides. There is other elements of code design. There is hardware and hardware code design. And one example for hardware and hardware code design is GPU Direct. And GPU Direct is a technology that was created by having companies on the network side and on the GPU side sit together, understand that there is a bottleneck in the connection between those elements. And by understanding that and collaborating together and now creating an hardware interfaces that essentially do code design between hardware elements, GPU Direct technology was created, which enable 10x of performance improvements. So that's one example of 10x. There is also software and software code design. And I'm going to talk a little bit later about OpenUCX as an example for software to software code design. And today, one of the issues is that there is multiple software frameworks. And I think DK talked a little bit about some of them, for example. And each one of them has pros and cons. And when you look into moving forward, it's not that we need to see if we need to create another one. In order to get the Exascale, we need to go into making unification of frameworks. And OpenUCX is one example for that. And of course, collaboration between industry and universities and academia and others to bring the knowledge of each into one area is essentially in order to build solutions based on code design. So one example, or one of the issues that we are facing now, which is covering the software and hardware code design. And here I'm looking into the relationship between frameworks, software frameworks, and then the underlying hardware elements. So again, if we go 10 years ago, and we look into what were the network latencies in that time, and they were running in around 10 microseconds of latency. So if you look on latency within a system, adapters, switches, essentially the latencies were in the 10 microsecond. The framework latency, if you look on MPI collective operations, for example, those framework operations were running in hundreds of microseconds. So then the hardware part was 10%, which is a big factor at the end of the day. Moving 10 years forward to today. Today, network devices are running in less than 100 of nanoseconds. So we got a 100x improvement just there. The communication frameworks and collective operations, and I'll give you some graphs later, are running today in tens of microseconds. So there was also a good improvements in that area. Now moving to the future, if we're talking about hardware network hardware that runs in hundreds of nanoseconds, and a communication framework that runs in tens of microseconds. Even if you take the network latencies to zero, you broke the law of physics. It's negligible if you look on the framework perspective. So instead of running in tens of microseconds, it will be 10 of microseconds minus 100 nanoseconds. That's not going to change anything. So now the question, how do we achieve another 10x of performance improvement for the next generation, knowing that the network interfaces will not go lower than that substantially? You know, you can cut another 20 nanoseconds, another 30 nanoseconds. That's not going to make a big change. So how do you make that change? And making that change requires you to go to co-design. So this is few examples of collective latencies, and we're talking about tens of microseconds here for those operations. So again, just focusing on the network part will not make that a 10x, or will not enable here 10x in performance improvements. So how do we go there? We go there with a co-design. So if the view so far was we run everything on the CPU side, the CPU is doing the management, the computation, the networking, everything is there. We're essentially relying on the capabilities of the CPU. Now, increasing the frequency of the CPU can help you there, but we're not there anymore. And adding more and more cores in the CPU will not help you there anymore because you're not increasing the frequency of the CPU. You have more and more core because you want to run more and more processes. That's not going to cut the latencies. So in order to get a 10x performance improvement, you need to start looking at the entire elements in the system, including the GPUs, the FPGAs, the adapter cards, and the switches, and that covering all, and you can also add the storage, covering all the active elements within the system, and take the framework, communication framework, and map that on every active component. There is no reason that the switch network will not start moving and doing in-network computing, essentially to go and reduce latencies. And even looking, years from now, there is nothing that's going to hold us to start putting things in the cables themselves, which now seems stupid, but also the cables will become an active components. So once you start doing those kind of mapping and doing computations in the CPU, computations in FPGA, in the GPU, and doing computations in the network as part of in-network computing, now you can take those frameworks and collective operations and reduce the latencies by 10x without saving that on the network, which doesn't exist from latency perspective. So this is an important task, and there is a lot of NRE funding that comes from government institutes out there to multiple companies to achieve the in-network computing or in-cluster computing, taking advantage of all the active components. We are aware of some of the developments, and we are participating with some of the developments out there. And we do expect that next year, or toward the end of the year and throughout next year, there will be multiple announcements on new solution based on the co-design that essentially enables the next 10x of performance improvement. Now, that will continue, and we'll see more things coming and mapping frameworks on all active devices in order to achieve a 10x from generation to generation, which will enable us to go to the exascale. So there is multiple elements underneath the co-design. Essentially, it's all covered under offloading technologies, which is offloading things that traditionally were run on the CPU and it cannot achieve reduction in latencies anymore, and map them on all of the other active devices. Software-defined X, it's part of that mission to bring things on. Direct communication between devices. I listed multiple things here, also listed virtualization. I'm happy that DK talked about virtualization before, so I'm not going to be the first one mentioning virtualization in an HPC meeting. Years ago, if someone would say virtualization in HPC, probably would kick out of the room. But looking ahead, one of the key issues is resiliency. or reliability in systems. And systems are growing in size. So it doesn't really help you that you have more and more devices. You just increase the probability of failing devices. So how can you solve something like that? Today, people are using checkpoint and restarts. It's great for storage vendors, for example, but still, you save a state and then you need to bring it again if something failed and start from that point, and again you need to save the state. That's something, this element cannot scale. Now, if you are able to bring virtualization in HPC, not in the sense of running more workloads on a system because it's not fully utilized, this is not the case here, but bringing virtualization in the sense of separating the hardware from the software. And if you're able to separate the hardware and the software, if something fails from a hardware perspective, you can continue to run the software and on different elements that you can bring on. So this is the key of virtualization. There is an effort, and DK, sorry that I'm mentioning your name so many times here, but DK did mention some of the work, and we had presentations in previous meetings of other elements. There is an effort to minimize the overhead of virtualization. And that's by going direct from guest machines to the hardware levels. And if you minimize the overhead there, and you go to a single percentage and even lower than that, then essentially you solve the problem from putting virtualization in HPC, and you are enabling now a new way to deal with resiliency and reliability for large systems. So this, yes?
So if we think about these days, and what you mentioned, the overhead that virtualization could deliver, solutions like Docker, is it something could be taken into consideration, especially in these days?
Yes.
Docker is one element. SIOV, for example, and then is another element. I think there is multiple elements, and you're right. There is an effort, and Docker is one example of reducing the overhead of virtualization, right? And if you go to overhead that it's negligible, suddenly you open a new way to deal with reliability issues and resiliencies. So that's why we see Docker, that's where we see other things, essentially trying to go and bring that capability into HPC. So that's around co-design. I wanted to give you a few other examples. This one is a software and software co-design. And I want to talk a little bit about Open UCX and what essentially it is. So starting with a simple joke, we're in a situation where you're facing multiple standards there, multiple software standards, and then there is always few people that get together and says, well, there is like 14 standards out there, it's too much, right? We need to create something that unified everything, and after that, the situation that you have 15 standards out there. So the goal is not to create another framework, another standard, and add another option of the software side. The goal about software and software co-design is actually reducing those elements. So what's Open UCX, or what UCX is? UCX is a collaboration between industry, government labs, and universities to take development that was already started in multiple areas that resulted in different frameworks and combine that into one. So that's actually doing unifications of framework. And the second goal is to minimize the overhead of software framework by getting closer to hardware interfaces and implemented multiple advantages there. And this is going again to the software and hardware co-design. So UCX essentially is a middleware that sits between the hardware on one side and then the programming level on the other side, if it's MPI, OpenSHMEM PGAS, UPC, or other things like that. The goal of UCX was to first deliver an API that is rich and enables all of those elements that were developed by other frameworks. Focus on performance. So minimizing your software overhead and getting those framework that runs on top of that to be able to access hardware level as low as possible. It's a community driven. I'll show you who's acting right now, and to support cross platforms. So to support any platform out there which enable people to use the same element for different hardware interfaces. There is different frameworks for UCX. I'm not going to go into details here. UCX has its website, openucx.org, I think, or .com, where you can go there and get more information there. Basically, UCX was created by merging 3 different frameworks that were created. Oak Ridge is one of the organization part of UCX. Oak Ridge were working on an interface called UCCS, which was their framework supporting SHMEM over their systems. IBM was working on PAMI, which was their interface. Mellanox was working on MXM. University of Houston and Tennessee were working also on those elements. All of those companies and organizations pretty much connected here together and contribute all of those frameworks into creating one that will replace all of those, which is called UCX. UCX support all of the communication framework on one side and then supporting all of the hardware interfaces on the other side. So there is support for standards like InfiniBand and Ethernet, support for Gemini and Aries on Cray, support for shared memory, and support for any other hardware interfaces that exist or will exist. So mapping some of the key companies or organization there, again, each one of those contributed its own developed framework into one, which is called UCX, and then UCX become the next generation framework for those guys. Argonne, Los Alamos, Lawrence Livermore recently joined that effort as well, bringing their capabilities, their experience into the organization. And that organization is growing in the number of companies, organizations, universities, government labs that bring their knowledge and their development software into creating that unified framework. So again, openucx.org, the information is there. The framework is also open, and it's open source. So some of the key parts in that framework were originally closed source, and now everything becoming an open source here. Another example of co-design which I mentioned before, which is a hardware and hardware co-design, and DK did talk greatly in details about the GPU Direct, so I'm not going to touch about that. But that was another example of achieving 10x performance improvement once you go to a co-design. So that's the key element around co-design, achieving a 10x performance from generation to generation. The last one I did mention music in my talk in the morning. Essentially, you can also look on that as some sort of co-design of bringing new capabilities into HPC, and then also looking how to take the software that was used there and connect it with the hardware, and with that you can achieve new things or new solutions. So again, I want to thank you for listening to the talk. There is more information that we're going to start putting out as part of the co-design examples. UCX is out there. You can go and learn about UCX, GPU Direct, and other things. And we do expect that several companies and the institute, the government institute that are funding them around co-design, will start to release new products in 2016, which will go strongly under the co-design and enable us to continue an increasing performance. Yes?
Yeah, my question is, what is the governance model? Who decide or which decide in each different topic? What is the way to go? Or how you can achieve in all these interrelated topics? What is the priority and what is the time frame to achieve the priority and to put all these different institutions in the same page?
Okay, so from a schedule the easier answer, or the easier part here is the schedule perspective. If you put a goal to get to the exascale in the 2020 to 2022, for example, and you look into what's the frequency of new generations of solutions being out there, you understand that in order to get there, you need to create a 10x performance improvements in the next 3 generations in order to go to the exascale. So schedule perspective is simple to understand. Now, how do you create the code design development and you understand, okay, this is a bottleneck, this is a bottleneck, this is a bottleneck. And I give you one example of the latency bottleneck, right? The latency wall, that in order to break the latency wall, you need to move to a code design. So there is multiple government-based projects. I know more details about a couple in the US, where there is a combination of government laboratories and major companies out there that do sit together and put plans in order to go to the exascale. And throughout the discussion there, they understand what are the bottlenecks, what needs to be done next. And this is how those combined group of people makes the decision about, okay, we need to do this one next, we need to do this one next, and we need to do this one next. And then there is funding that goes to those companies in order to develop or accelerate the hardware development, as well as the software side. Sure. Any other questions? Okay, thank you very much.